All right, can people hear me okay?
Yes.
So 1 minute elevator pitch. I'm Jasper. I like trail running and dogs. I live in Iowa. I work at the University of Iowa, and I build instruments to measure charged particles and send them into space and measure whatever cool things we can find in space. So that's kind of the lines of what I'm going to be talking to you about today. I think that was more of a 30-second elevator pitch, but hopefully that's close enough. Oh, it was on there. So when Nick asked me to give this talk, he gave me the title, which is Observational Heliophysics, Particles, Plasma, and Fields, I think, or some permutation thereof. And I said, well, isn't that kind of everything? How am I supposed to talk about that in an hour and a half? But I will do my best. And actually, I'm hoping this will take something less than an hour and a half, so we'll have some time for discussion and questions and so forth, because I think that's sort of the main point of being here. So let me just start with a little bit of, where should I point this so that it will register? Oh, apparently something worked there. Okay. So why don't we just take a nice voltmeter and a wind gauge and an anemometer up into space and call it good. We know how to measure things like winds and pressures and voltages and currents, right? Why is it so hard to do this in space? Well, I thought it would be useful to start with just a couple of real numbers and get people kind of thinking about how different these real numbers are than things that we're used to on the ground. So if you think about your favorite plasma, let's say the solar corona, it might have a temperature of a few million degrees Kelvin, a little bit hotter than what we're standing in today. The canonical solar wind speed is 1,000,000 miles per hour. I know, imperial units, sorry, but it sounds way cooler than whatever it is in kilometers per second. Solar wind ram pressure is about a nanopascal. You know, you're used to thinking about pressures that are on the order of pascals and more. Plasma density in the magnetosphere might be a few hundredths of a particle to a few thousand particles per cubic centimeter, depending on where you are, what region of the magnetosphere. We're standing in, I had to look it up, I didn't know this number, 2.5 times 10 to the 19 particles per centimeter right now. So the densities of particles that we're talking about are wildly different from what they are in an atmosphere. Electric and magnetic fields are also different than what we're used to. Typical motional electric field in the solar wind is a millivolt per meter. That means you need to go a kilometer to get as much voltage as you get across like a AA battery. And that's the perpendicular electric field. The parallel electric field is orders of magnitude weaker than that, a nanovolt per meter. And the magnetic field is similarly very different. We're standing in something like 50,000 nanoteslas right now, but out in the solar wind, it might be a nanotesla or 10 nanoteslas. So the measurement techniques that we have on the ground don't necessarily work for measuring things in a space plasma. Okay, so what do we have to measure to actually understand a space plasma? I suspect what I'm going to talk about for the next 5 minutes or so will overlap a little bit with things that people talked about in the last couple of days, but that is no bad thing. So to describe a plasma, what do you need? You need the equations that describe the electromagnetic fields, Maxwell's equations. Those equations have the fields, they also have sources. You see a rho there, you see a J there. Those are charge density and current density. That's where the particles come in. You can relate those to the particle charges and the, densities and the velocities, like so. And then these fields that are described by Maxwell's equations themselves exert forces on the particles. You have Lorentz forces. You might have some other forces in there like gravity and things like that. You might have some collisions between particles, but there's a rather small number of equations that you could use to describe everything you care about in a space plasma. But this is not how we do space plasmas because there are just too many particles. There's a couple of dragons hidden here, by the way. You've got a D and an H in here, which are the fields in material. So there are all sorts of interesting things that happen when you have a medium that the fields are part of. And that's very, very relevant in plasma physics, but that is about as much as I'm going to say about that until we talk about magnetometers. Okay, we don't think about plasmas in terms of individual particles most of the time, though, because there's just too damn many particles. So I really like this graph that shows kind of every plasma that you can imagine. The axes here, the horizontal axis is the density of the plasma, the vertical axis is the temperature of the plasma, and there are some useful dashed lines drawn on here. The lines that are going like that, the kind of orangey red lines, those are the Debye length of the plasma. The Debye length is a characteristic scale over which any charge imbalance is screened out by the effects of the plasma. So it's just kind of a convenient length scale of the plasma. You can see in the kind of plasmas we're probably mostly talking about here, you've got a Debye length of meters to perhaps kilometers. Within a sphere with the radius of the Debye length, these other dark blue lines show you how many particles you have in a Debye sphere. And it's hard to read the numbers on here, but you're talking about numbers of like 10 to the 12, 10 to the 9, 10 to the 15. So in something like the solar wind, your Debye length might be a meter, and within a sphere a meter in size, you've got somewhere between 10 to the 9 and 10 to the 12 particles. So we can't deal with individual particles, which means that we have to take a statistical approach to understanding a plasma. So I know, because I looked at the slides that were presented the last couple of days, that you've been introduced to the concept of the distribution function. The distribution function is just a probability distribution, but it's a strange probability distribution because it is 6-dimensional. It is a function of 3 dimensions of space, and it is a function of 3 dimensions of velocity. But across all those dimensions, it's just a probability density. So in a couple of dimensions here, imagine that you have a point cloud in terms of whatever 2 variables you want. These could be positions or velocities. And then the distribution function is essentially the density of that point cloud. It has units, which sound strange, of particles per cubic meter per cubic meter per second. It's a weird kind of a set of units, but that's because it is a function of 3 coordinates of space and 3 coordinates of velocity. So the distribution function is really what we're trying to measure. And if you have the distribution function, then you can use something like the Boltzmann equation to understand how that distribution function evolves. This is essentially analogous to the Lorentz force equation, but it's applied to a probability distribution function instead of an individual particle. Once you have the distribution function, you can get back to all the quantities that you're used to thinking about, because all of the macroscopic moments of the plasma, things like density, average velocity, average temperature, are all just weighted averages of the distribution function. So if you want to calculate the particle density, all you have to take is take the distribution function and integrate it over velocity. So you're averaging the distribution function over velocity, you're just counting up the total number of particles, and you end up with something which is a particle density, something like particles per cc or particles per meter cubed, depending on which you prefer. If you want to get the average velocity of the particle, you simply take the weighted average of the velocity, that gives you the total flux, divide by the density, and you get the average velocity. And you can go up to higher moments, you can calculate pressures, you can calculate heat fluxes, so on and so forth. So if you have the distribution function, you can get back to the moments that are easy to think about. But plasma physics is so much more than the distribution function, because distribution functions in space plasmas tend to not be simple Maxwell-Boltzmann distributions that can be easily described in terms of a density, a velocity, a temperature, things like that, there's higher order structure to those things. If you have a sink of particles that absorbs some of your particles, you might have something like a loss cone distribution here, where your nice circular contours that you would have for a Maxwellian have bite outs. This is what you will commonly see when you have particle distributions on closed magnetic field lines like those of a magnetosphere. And it doesn't take much of a perturbation to a Maxwellian distribution to cause interesting plasma physics to happen. One of the most amazing things about plasma physics is that if you take a distribution function and you perturb it just a little bit, then magic happens. So if you take a quasi-Maxwellian distribution function and you add a little bump here, and a little bit of an excess of particles at high velocity, and you let this system evolve, you can see that here's your main bump here of the distribution, here's your little bump on the tail, and you let this system go, and it starts to oscillate. And if you look at the energy in the fields as a function of time, you're seeing that energy is going from the particles into the fields, and then it's kind of sloshing back and forth. The energy in the electric field here is actually oscillating, so you've got energy transfer back and forth between the particles and fields. And so this is the magic of plasma physics, and this is why it's hard to measure plasma physics, because if you want to understand this, you need an instrument that will not just measure the moments of the distribution, but measure this structure of the distribution function and tell you that this bump on the tail is there. Just for fun, here's an exaggerated version of this. This is the two-stream instability, where instead of having a little bump on the tail, you have two populations, two bumps that are the same size. And if you watch this evolve, this is now a 2D phase space diagram. The horizontal axis is position, and the vertical axis is velocity. And so you're seeing the blue population going one direction, the red population going the other, but they're mixing and forming a vortex here. And if I talk long enough, this will circle back around and you'll see the initiation of that, which is really cool when you see all those particles start to mix in phase space. So this is the magic of plasma physics, and this is why we want to measure charged particles and why we want to measure the fields that are created by and also guide these kind of phenomena. All right, so let's get into measuring particles. I'm a particle guy, so I'm going to start with the plasma and particles, but we will hit the fields instruments at the end of this. So the first thing you can do to measure a space plasma is to measure a current. You put something out in space, and you might think, okay, the plasma is neutral, so that means that there's not really going to be a current to a sensor. But one thing that's interesting about a plasma is that it is typically composed of ions, which are big and heavy and slow, and electrons, which are light and fast and zippy. And that means that even if you put a probe in a completely neutral plasma, you will typically get a current to it, because you'll get electrons bombarding it very quickly, and you will get a current to that. So you stick a probe out in a plasma, and there will be a current. But then what happens if you take your probe and you change its voltage? You make it a little bit positive relative to the plasma. That repels the ions, sucks in some of the electrons, or you make it a little bit negative compared to the plasma, try to repel the electrons and pull in the ions, and you get a curve that looks something like this. Hitting the wrong button here. So this is voltage on the x-axis, this is current on the y-axis. And if you understand the plasma that you're measuring and you have a good model of your probe, you can take that curve and you can use it to tell you things about the density and temperature of the electrons and the ions in your plasma. There's some subtleties here because it depends on whether your probe is small or big compared to the characteristic length scales of the plasma. So in like a lab plasma, it's really hard to measure things on the scale of the plasma because the Debye length is really tiny. So you make the smallest possible probe that you can stick in there, and it's still kind of big compared to the Debye length. One thing that's cool about space plasmas is we can actually make a probe which is small compared to the Debye length. And that means that the curve of voltage and current that you get is different, but it also means that you can really sample the fine structure of the plasma. So here's an example of a Langmuir probe. I picked this instrument because it was built around the corner from here at LASP. This is the Langmuir probe wave instrument from the MAVEN spacecraft. And what you're looking at here is kind of a deployment mechanism. And then the active element here is this long rod, which has been deployed out. And that's simply just sitting there in the plasma, and you're biasing the voltage of it up and down and measuring the current that you get in response. And from this, we get beautiful data on electron density and temperature in the Martian magnetosphere and ionosphere. So you can look at some different ways to do this. If instead of just a plasma kind of floating around in space, you have a plasma which is either flowing, or you have a spacecraft which is going rapidly enough through the plasma that it is effectively flowing, then you might use something like a retarding potential analyzer. This again is just measuring current, but it's measuring current in a directional sense. So imagining that you have a flowing plasma, then you have plasma flowing into your aperture, and you can do the same kind of trick that you do with the Langmuir probe. You can change the voltage of your aperture. Typically, you do that with a retarding grid in between some grounded grids so you don't muck up the plasma around yourself, and you get a curve of ion flux as a function of retarding voltage, and that tells you things about the density and the velocity of the plasma. So here's an example of that. This is an instrument that was flown on a terrestrial mission looking at ionospheric ion density and velocity and temperature and so forth. And you can see that it's very simple. It's just a current collecting element and a bunch of grids held at various potentials. These grids are there to do things like stop secondary electrons created from surfaces from creating a current that you don't want, and all sorts of second order effects. But basically, you're just measuring current. So measuring current works pretty well if you're in a relatively dense plasma, where you can get large numbers of particles and measure them as a current using electronics that are buildable in a lab. But if you go into a more tenuous plasma, it becomes very, very hard to measure a bulk current, and you have to instead rely on measuring individual particles. Before we get to that, I'll mention one more iteration on measuring current. So this is a Faraday cup, and a Faraday cup is almost the same thing as a retarding potential analyzer with one subtle tweak. Instead of just sweeping the voltages of your grid up and down, what you do is you put a modulation on that voltage, and that has the result of modulating the signal that you get. And the amount of signal that you get depends on how many particles there are with an energy in the band that you're modulating your voltage across. So what you get out the back end of this is you get, too fast, you get a current signal with a variable amplitude, and the amplitude tells you something about the height of the distribution function. So this is a beautiful technique which has been used in space plasmas a lot, because by measuring the height of a modulated signal, what you're able to do is be completely immune to any constant background. So if you have some kind of a background in this sensor due to other particle populations that you don't want to measure, or due to some kind of electronics background or something, those won't be modulated at the frequency that you're looking at. And so you do some kind of a lock-in amplifier on the frequency of your modulation, and you get a measurement which is much less susceptible to background. So this is kind of a beautiful technique. To do this in a tenuous plasma, you have to have a really big cup, though, because you have to collect a lot of current. So this is a good technique in the right kind of plasma, but it's not always exactly the right technique. It also is basically a one-dimensional measurement, right? So you've got particles coming into your aperture. You can play some tricks there by taking the collecting plate that you have down here at the very bottom and segmenting it, and that allows you to get some directional information. but it doesn't give you a lot of information about the higher order spatial structure of your distribution function. Still, measurements of this type are really awesome. This is the Faraday cup that was flown on the Parker Solar Probe. This is a particularly interesting Faraday cup because it had to basically sit out in the breeze and soak up the full illumination from the sun at 10 solar radii. So we had to use a lot of exotic materials to build this instrument. Lots of metals with funny names like molybdenum and tungsten, not your normal everyday aluminum and steel. Where you would normally use plastic for insulators, we used sapphire. So this is a wild instrument, also not a cheap one. Okay, so there's another way that you can measure the distribution function or sample the distribution function, which is to measure individual particles. So I'm going to talk about a bunch of different ways now to basically count particles. And there's a lot of physics to doing this because to count particles, you need some kind of a detector. And there is a lot of physics in detectors. So the first kind of detector I'm going to talk to you about is a solid state detector. So if you take a solid state material and you dope it so that it either has a large amount of holes or a large amount of electrons or a depletion of one of those, you can make it into a detector. So if you set up a solid state detector in this way, what you can do is you can set it up so that when a particle comes in, if it has enough energy, it creates electron hole pairs in your material. And then if you put an electric field, doesn't have to be a very big electric field, 50 volts, 100 volts will do it. You put an electric field across that region, then it will pull the electrons one way, it will pull the holes the other way, and if you put a little charge-sensitive amplifier here, then you can collect a charge pulse from that. And the cool thing about this measurement is that the number of electron hole pairs you get to first order is proportional to the energy of the particle that comes in. So it gives you a count when a particle comes into your material, but it also gives you an energy because the amplitude of your charge pulse is proportional to the energy of the particle. So that's a really cool measurement. It's not a perfect measurement though, because there's something called pulse height defect, which is basically not all of the energy of the incoming particle goes to creating electron hole pairs, and the amount of energy that goes to electron hole pairs depends on things like the mass of your particle. So this is an older instrument here, but a good one. This was flown on Ulysses, and what this is showing you is the detection efficiency as a function of energy for different masses, different species of ions. The solid line here is the protons. Protons lose less of their energy to things other than creating electron hole pairs, and so your efficiency for protons is pretty good, close to 100% once you get above a threshold energy. But as you go to higher and higher mass species, by the time you get up to argon, you can see you have to have a whopping big energy before you get anything out as far as a charge pulse, and the efficiency is a lot less. So it doesn't mean that you can't use these sensors to measure heavy ions, but it means you need to do a lot of calibration to understand what the current signal that comes out tells you about the initial energy of this particle. So a lot of calibration goes into these kind of sensors. I'm not going to talk about the details of this formula, but there is a formula which tells you something about how much energy a particle loses when it goes through matter. Question? Sorry, I can't hear you well. Can you...
Ready?
So my my question is, why do we need two different instruments to measure current, like a Faraday cup and the probe?
Why do we need different instruments to measure current? Why don't we just use a single instrument to measure everything? Is that basically the question?
So for example, on Parker Solar Probe, I'm not sure if there's only like a Faraday cup only, or Faraday cup and probe.
Yeah, well, it's a really great question, and there's not a single answer to it, but I'm going to give you kind of a general answer, and then I'll talk specifically about Parker Solar Probe. So the general answer is that no single instrument will measure everything in a space plasma, because you would have to measure over an entire range of energy, and you would have to measure particles coming from all directions, 4 pi. It's hard to build an instrument that measures 4 pi steradians, and you would have to be able to measure signals over a very wide dynamic range, because to measure both the middle of the Maxwell-Boltzmann and the wings way out here is usually a big dynamic range. So it's almost always impossible to measure all the different parts of a distribution function with a single instrument, especially if, like Parker Solar Probe, you're going through a wide range of environments as you go close to the sun and far away. On Parker Solar Probe, what we actually had was around a half dozen different instruments that measured charged particles. So the Faraday cup does a very good job of measuring the solar wind when it is coming kind of directly into the aperture and when the cup is not too hot. So the Faraday cup on Parker Solar Probe actually does a beautiful job until we get really close to the sun. And then what happens is that the spacecraft is basically in orbit, and when you're close to the sun, the orbital velocity is going sideways. And what happens then is it's like the rain on your windshield when you're driving fast. It's not coming straight down, it's coming in at an angle. Faraday cup starts to do not so well in that configuration. So we have another set of instruments. I'm going to talk about electrostatic analyzers in a little bit, but those have a broader field of view, and they're able to measure the distribution when the particles are coming in from the side. Then we have a whole other set of instruments which are measuring the energetic particles, which you can think of as the far tail of the distribution. Those have such low fluxes and such high energies that we can't measure them with the same sensor. I hope that goes some way towards answering your question. It's a really good one. Okay, so particles lose energy and matter. That's a pain, because it means that when you measure something with one of these detectors, you have to take that into account. But there's a way that you can flip that around, and you can actually use it to your advantage. So if you can have not a single particle, but a stack of particles, what you can do is measure not just the energy, but how fast the energy is decreasing as a particle goes through the material that you're detecting it with. So the particles the plots that you're seeing here, the horizontal axis of both of these plots is energy. The left-hand plot, the vertical axis is actually dE dx, so it's the rate at which you're losing energy as a function of distance as your particles go through your material. The plot on the right is almost the same thing, but it's just dE, not divided by dx. So that's why the curves that you see look convex in one case and concave in the other, but they're showing you the same thing, which is that if you plot measurements in this space, and you can measure both energy and rate of energy lost, then the elements get separated. So over here you've got some nice lab data. You've got things like boron and carbon and nitrogen and oxygen that are easy to produce in a lab, and you can see that these produce different curves in this space. So if you can locate a particle in this space, you can tell not just what energy it has, but what mass it is, which is very useful when you're measuring a multi-component plasma. Over here is data from space. So lots of hydrogen and helium in space. Hydrogen is essentially off the corner of this graph, but here's helium, and then you have things like carbon, nitrogen, oxygen, neon, magnesium, silicon, all these things coming out of the sun, and all nicely separated. So this technique works really well in a regime where you've got a lot of energy. So you've got enough energy to make it through a stack of these detectors and give you a real measurement. And you also can't have too high of a flux of these particles because the electronics to do this are very slow. So this technique has been successfully used in space for a long time. These are instruments from the ACE spacecraft, which is something like 20, 25 years old now. You can tell they're old because the images are really grainy. I tried to find some better pictures, but I failed. But you can see the typical kind of thing that you have here. Each one of the little bumps on these like colanders here is an individual sensor. So this is essentially a telescope with a bunch of eyes that are looking in different directions, measuring the energetic particle fluxes that are coming in over a range of different directions. Again, trying to sample different parts of the distribution function. Over here are some other energetic particle telescopes, which are more of the DEDX variety, measuring energy loss through a stack of detectors. So there are advantages and disadvantages to this. You can do some cool things with these detectors. You can measure not only particles local to our heliosphere, but you can measure things that are coming from outside of our heliosphere. Did I see a hand over here? Question? Good catch.
So does solid state detector separate ions based on mass or mass per charge? And follow-up question, if it's mass per charge, is there, I guess it's like a off-site question, but is there a way to separate ions with the same mass per charge but different masses?
Same mass per charge, but different masses. So if you're going to use the E by DEDX technique, if you go back to this beta block formula, it does depend on things like mass and charge. And if you look carefully at a couple of these curves, you can see that there are actually different curves here, even for different isotopes of the same element. So it does give you mass separation. It can, in principle, tell you something about different charge states, but that gets to be a harder and harder measurement to make. It's actually easier to separate mass than it is charge with one of these solid state detectors. There are some other ways we'll see later on to detect mass per charge, though, so you can kind of combine these techniques to get both mass and mass per charge.
Okay, thank you.
Yep. Good questions. All right, so if you've got energetic enough particles and you've got not too many of them, then solid state detectors work really well. But if you've got a lot of particles, but not really enough particles to make a current that you can just measure a current, then there is a class of instruments that uses other types of detectors. And these detectors depend on something called secondary electron emission, which is essentially that if you hit a surface, it tends to knock electrons off of it. And if you can find just the right kind of material, you can find a material where if you hit a surface with a single electron at an energy of tens of eV, you will actually knock more than one electron off of the surface. And then what you can do is you can create a cascade process. So there's a whole class of detectors that uses a secondary electron cascade as a measurement device. So why do you need this? The reason that you need this is that when your incident particle comes in, say it's an ion, say it's an electron, it doesn't matter. It has an elementary charge, or maybe if it's a heavily charged ion, it has multiples of the elementary charge. There are no electronics that have ever been built that can measure a single charge and turn it into a digital signal. No electronics that have ever been built for a space instrument, at least. I should be careful. It's extremely hard. Typical electronics, you might be doing really, really, really well if you can measure a charge pulse of like 100 electrons. That would be very sensitive electronics. Electronics that will measure a charge pulse of 100 electrons, though, take a long time to do it. And so they don't allow you to measure very fast. What you'd really like to have is a charge pulse of like 1,000,000 electrons. That's a charge pulse that you can measure and you can do it quickly. So these detectors give you the capability to take a single particle coming in and turn it into a charge pulse of 1,000,000 electrons. And the way they do it is just a secondary electron cascade. So you can see it schematically here. Ion comes in, creates some secondary electrons. Each of those creates some more, and so on down until you get to the bottom and you get 1,000,000 electrons coming out the bottom. This case here is set up as individual conversion dinodes, individual surfaces that create secondary electrons, but you can also just have a continuous surface. So this is a CEM, charged electron multiplier, and the trumpet up here at the top is where the incoming particle comes in, and then it creates a cascade of electrons, and by the time you get out the bottom, you've got 1,000,000 electrons that you can put into your electronics, measure it as a charge pulse, create a digital signal. So CEMs are commonly used in spaceflight instruments as detectors. There's another cool way that you can do this, which is to create what's called a microchannel plate. So the way you make one of these things is actually really, really cool. You make essentially little glass tubes which are doped with a lead material that has high secondary electron emission characteristics, and you form it into a matrix, kind of a honeycomb shape, and then you heat it out and you draw it out, and you make it very long, and you make those tubes very small. Each of the tubes that you're looking at here on the screen is, a fraction of a millimeter across. So this microchannel plate that you're looking at here is about life size on the computer screen here. It's a couple inches across here. You can see the individual microchannel plate tubes in there. So this is the top view of something that looks like this in cross-section, which has a whole bunch of individual tubes going through here. So if you put one of these things as a detector, a particle comes in, and if it hits one of the open pores, it'll knock an electron off of there, create a cascade, and by the time you get to the bottom, you've got your 1,000,000 electron pulse that you can register with your electronics. These kind of detectors are used a lot in optical instruments, by the way, because they detect photons just as well as they detect electrons or ions. In fact, the drawback of these detectors is they detect everything. And that means you've got to put something in front of them if you want to actually know what you're measuring. So in front of one of these kind of detectors, you need to put something that will tell you what you're actually measuring. So one thing you could do is you could put some magnetic fields in front of that. Magnetic fields will separate species by mass and by charge, because the gyro radius depends on both mass and charge. So if you put a magnetic separator, then you can take an incoming particle beam and you can split it into different masses and charges, including electrons and ions, of course, which have radically different gyro radii. So this is one way that you can pre-filter your particles before they get down to your detector. This method of measuring is not very popular with your friends on the spacecraft, though, because your friends on the spacecraft want to measure the magnetic field, and this thing produces a whopping magnetic field that is not the magnetic field of the plasma. There are some ways you can get around this by, compensating magnets and pairing magnets to cancel out dipoles and things, but it has some drawbacks. Another way that you can do this, which is what I do for a living, is you can use electric fields to do this. So if you put two concentric surfaces, hemispheric is the usual way to do it, but in principle, any set of surfaces will work. You put an electric field between them, and then it acts as an energy selector. So first of all, if you have the wrong sign of charge, it will bend the wrong way in this electric field, won't make it through your aperture. If you have the right sense of charge, it will bend the direction that you want it to, but it has to have the right energy to make it all the way through, because what you need is you need the electric field between these plates to provide the centripetal force to keep your particle moving in a circle. So it's simple freshman physics. It's just QE is mv squared over r, but it works beautifully as an energy selector, because if you have a range of energies come into this, then the low energies get bent too much, they run into the inner wall. The high energies don't get bent enough, they run into the outer wall, and the ones that you want to measure come all the way down to your detector. And then what you do, of course, is you take these voltages and you sweep them, and it allows you to measure particles over a range of energies. Common way to do this is to make what's called a top hat electrostatic analyzer. So the way you make a top hat is you have an inner hemisphere, and then you put an outer hemisphere, but you have a hole in that outer hemisphere, and then above that you sort of complete the top of the hemisphere with an extra bit, which is the top hat. So up here at the top is the top hat, here's your inner hemisphere, here's your outer hemisphere, and then there's a gap here where the particles can come in from the sides. And this whole thing has rotational symmetry around the vertical axis here. So if you looked down on this from above, it would be a circle. And the great thing about this is that particles come into it and they follow a great circle trajectory between the two hemispheres. And particles that come in with the same direction focus onto a spot down here where you can put a detector. And so if you have a detector down here at the bottom, then by measuring where the particles land around here, you can determine which direction they came in from. So this gives you a 2D slice through the distribution function. If you're on a spinning spacecraft, you take that 2D slice and you spin it around and you get the full 3D. If you're on a non-spinning spacecraft, what you do is you put an extra set of deflectors in front of that out in front, and you steer your field of view up and down, and you don't quite get 4 pi, you get maybe 2.5 or 3 pi field of view. But by sweeping all of these voltages, you can actually cover the whole distribution function. So this is what I do. Here's just a couple of beauty images. On the left here, you see the instrument that I built for the TRACER spacecraft. On the right here, you see an electron and an ion sensor that I worked on for Parker Solar Probe. The electron sensor is over here on the left. The ion sensor is over here on the right. And you can see the ion sensor here has an extra little part below the deflector plates and the optics. And we'll talk about what that extra part is. It's a time of flight section. Question? Oh, toaster sized. To give you a sense of scale, this instrument right here is a CubeSat form factor. So the square top is 10 centimeters by 10 centimeters, and then it's maybe 18 centimeters tall, something like that. So they are big enough that they feel heavy, but they're small enough that you can actually lift and carry them around. Mostly the engineers don't let me lift them and carry them around. There are special processes for doing that, but in principle, you can lift them and carry them around. You know, occasionally on these projects, I graduate to the point where I'm allowed to run the tests and calibrations myself, but they never, ever let me touch like fasteners and bolts and stuff like that. Never let a scientist near an actual like torque wrench. What were we talking about? Okay, so a second ago I pointed out the extra part here. So the electrostatic analyzer is beautiful for separating particles with different directions and with different energies per charge, because it uses electric fields to do this separation. And an electric field treats, you know, everything with the same energy per charge the same way. but it doesn't a priori allow you to separate particles of different masses. So what you need is an additional bit of smarts to do that if you want to tell the different species apart, especially if they're all coming in at the same energy. So one way that you can do that is by using what's called time of flight. So if you start a bunch of ions with the same energy in a race, then the ones with higher mass will have lower velocity and they will lose the race, assuming they all start at the same energy. So what you commonly do in these kind of instruments is you do an energy measurement and then you do a time of flight measurement. And so you get the energy and then you get the mass from the time of flight and the energy together. So conceptually, this is easy to do. You just take all your particles and you start them at the left side and you wait until they get to the right side and you measure them. All you have to do is measure time, right? Time is the easiest thing in the world to measure. All you need to do is have a clock and, count time ticks. But time is actually hard to measure because you need to measure a start time and a stop time. So the magic of time of flight measurements is figuring out how to generate a start time and a stop time. One way to do that is to use very, very thin carbon foils. So this is an instrument from the MAVEN spacecraft, and what you're looking down on is you're looking on the time of flight section that comes after the electrostatic analyzer, and each one of these is sort of an inlet into that time of flight section. And you might notice that these inlets look kind of cloudy. And that's because there are very, very thin carbon foils there. So thin that you can actually see through them, but not so thick that an energetic enough ion won't go through them. In fact, when an ion comes in and hits one of these carbon foils, with high probability, it would actually go right through the carbon foil. And actually, with high probability, it will knock some electrons off of the carbon atoms in the foil, and it will create an electron pulse. And you can then use that electron pulse as a start time. So your ions come into the aperture here. They go right through and come on down to the bottom. But when they go through, they generate some start electrons, which you steer over here. The electrons move so fast that you can basically measure this pulse of electrons and call it your start time, and then you measure when the ions get down here and you measure your stop time. That gives you a time, that gives you a velocity. With a velocity and an energy, you get a mass, and voila, you have everything. There are other ways to do this. So carbon foils are not the only way to generate a signal. Another thing you can do is basically bounce your particles off of some kind of a surface. This now is more similar to what we do with microchannel plates, where we're generating secondary electrons. In this case, you can generate either electrons or you can generate positive or negative ions from conversion surfaces. So this is actually an interesting technique because it will work not only with charged particles, but with neutral particles. So the image that you're seeing here over here in cross-section, this is actually a detector which is designed to measure not charged particles, but neutral particles. So the neutral particles come in, they hit a surface, they gain an electron or lose an electron depending on the type of conversion surface you're using, and then you measure the charged particle. And you can do amazing things with neutral particle imaging because neutral particles go straight from where they were created and they don't feel all the electric and magnetic fields. And so you can use neutral particle imaging kind of like you would use a telescope. You can actually take pictures of processes in very distant locations. So this here is an image of the terrestrial system taken using a neutral particle imaging technique. So what's happening here is you have some kind of an energetic ion which is gyrating around. It hits a background neutral atom, say a hydrogen atom that's part of the terrestrial corona. They swap electrons and your energetic ion becomes an energetic neutral atom, which maintains the velocity that the ion had but it no longer feels electric and magnetic fields, and so it just follows a straight line trajectory, and it allows you to image the source distribution here. Other examples of this now is Titan. So you're seeing some kind of a hot interaction region here between Titan's atmosphere and the surrounding ions of the Saturnian magnetosphere, or is it Cronian? Never sure the right way to say that. And here's an example from IBEX, where you're looking at energetic neutral atoms that are actually created at the very outer edge of our solar system. So you're actually using essentially a particle detector, but it is allowing you to take an image of processes which are happening all the way out at the outer edge of our solar system. So I know you're going to be talking a lot more about remote sensing measurements in succeeding lectures, but just remember that sometimes you can use in situ measurements as a remote sensing measurement. So there's not always a clean separation between those things. Another thing that you can do, a couple more things I'm going to talk about here with particles before we get into waves. So another way, question? Go for it.
So there could be other sources of ENAs apart from geocoronal emission. It could be, say, the heliosphere or even other planetary magnetosphere. So is it possible to determine what the source is when you do all sky survey like you show?
Yeah, so it's a great question.
What are the
and
typical flux values if we want to compare?
Yeah, so what you need to create an energetic neutral atom is you need an energetic ion and you need a neutral for it to collide with. So those conditions are met in lots of different locations, right? I mean, they're met anywhere where you have a plasma that is interacting with a neutral atmosphere. In many of those locations, you don't get a lot of flux out of this process. So if you take your average neutral atom instrument and just point it out at the sky, you're not going to see much. If you could make an extraordinarily sensitive neutral atom telescope with extraordinarily angular precision, such that you could point it very carefully at some of these sources, then you could start to see lots of point sources out there. But mostly what you see with the neutral atom telescope is you see broad distributed things like the edge of our heliosphere. Because to date, these instruments do not have exquisite angular resolution. They have, 10-degree resolution or 20-degree resolution, things that make astronomers just laugh at us, right? Because astronomers are talking about, arc-second resolutions and things like this. So it's a little bit of a different ballgame. But maybe someday we'll have energetic neutral atom telescopes that have arc-second resolution and sensitivity that will allow us to see point sources. But right now, if you took an energetic neutral atom telescope that can be built and looked out, you would see things happening in our terrestrial system, and you'd see the outer edge of the solar system, and once a month you might see the moon. Great question. All right. I'm not going to talk too much about RF techniques, I think. I want to make sure I get to fields. So I'm going to skip through this one. To be complete, I'll say a little bit about dust sensors. So we've been talking about plasmas as being composed of electrons and ions, and that is indeed the typical kind of plasma. But there are various situations in our solar system where you can actually have dust particles that are part of the plasma. Dust particles can be created from cometary streams, from collisions out in the asteroid belt. Various things create dust particles in space. When you go into planetary magnetospheres, you can see dust particles that are created from, basically asteroids colliding with each other, breaking up, creating little dust particles, forming things like the rings of Saturn. In any case, if you are moving fast enough with respect to these dust particles, you can measure them. And the way that you do it is you have basically a big collector bowl, and you put an electric field between your collector and a detector over here, and when dust particles come in, if they are fast enough, they will basically produce a little impact plume. And if you put an electric field across here, you can sweep the ions and the electrons apart. You can measure the charge pulse to tell you that there was a dust particle there. And you can even, if you have a sufficiently complicated instrument, you can take the ions that are created in this impact plume and do a mass analysis on them, and you can determine what the dust particle is made of. There's some interesting things that you can do in space with dust measurements as well. Okay, let's get to fields instruments. I don't want to shortchange fields. All right, how do you measure a magnetic field? Well, measuring a magnetic field basically comes down to applying Faraday's law, but there's a couple different ways that you can apply Faraday's law to measure a magnetic field. So Faraday's law says that the EMF generated around a loop is minus the time derivative of the magnetic flux through your loop. So if you measure the magnetic flux, you can kind of break it up into its constituents. The magnetic field is some kind of a magnetic permeability mu times the magnetizing field H, the number of turns of wire that you're measuring a flux through, the area of those loops of wire, and you take minus the time derivative of the product of all of those things. So your sensor, unless you have something really exotic, is a fixed geometry. So the number of loops and the area of the loops is constant. But you could imagine that you could either vary the external magnetic field, so you could have a dH dt term, or you could vary the permeability of your sensor perhaps, and you could have a d mu dt term. So how do you vary the permeability of your sensor? Well, if you use something like a ferromagnetic material, then the cool thing about a ferromagnetic material is that there is not a linear relationship between the magnetizing field and the magnetization of your ferromagnet. And that's because ferromagnetic materials like to organize themselves in domains. So if you take kind of an unmagnetized ferromagnetic material, it tends to have domains of coherent magnetization. This has to do with quantum mechanics and spin-spin interactions and things that are far too complicated to talk about. But in any case, you have these individual domains. If you put an external field across this magnet, you can force those domains to align. So if you start with an initially unmagnetized magnet, you put a strong enough magnetic field across it, you can force those domains to align, and you can take it into what's called saturation. You let that field go, and it doesn't relax all the way back to zero. It has a memory, right? So if you take your fridge magnet, it doesn't have a zero magnetic field in its quiescent state. It has a magnetic field, and that's because the material has some kind of a memory. So when it relaxes back to a particular state here, it retains a remnant magnetization. If you take the field the other direction, you can wipe that out, and you can even impose magnetization the other way, and so on and so forth. For our purposes, there are two important things about this plot here. One of the important things is that it has a memory. It has what's called hysteresis, but the really important thing for our purpose is that it's not just a straight line. So if this was what is called a paramagnetic material, you would just have a straight line relationship between B and H here, but you don't. You have this kind of a weird curved relationship where you can take it all the way to saturation and it flattens out, or you can take it back the other way and you can saturate it the other way. So there's a common way to think about how fluxgate magnetometers work, which is to imagine this loop of magnetic material here. This is the fluxgate. Imagine breaking it up into two halves, a left half and a right half. So please understand there's not actually anything different about the two halves. This is a way to kind of think about how a fluxgate works. If you do that, then imagine applying an oscillating magnetic field to this magnet. So you're going to have some kind of a drive voltage up here. And if you have no ambient magnetic field, everything's going to be completely symmetric. So you're going to take your magnetic material up to saturation, down to saturation the other way, up to saturation the other way, but the two halves will cancel out perfectly. So the blue and the red curves here are like the two halves of your flux gate, and when you add the two of them together, you just get nothing. But now imagine there's something besides just the drive field that you're saturating this thing back and forth with. If there's an external field, then this breaks your symmetry. So on one side, you add an external field. On the other, you subtract it, and you get an asymmetric response of the two sides of your flux gate. So the one side of your flux gate now is asymmetric one way, the other side is asymmetric the other way, and when you add these together now, you get a net signal. And notice that that signal is at twice the frequency of your drive voltage. So this is what's called a second harmonic flux gate magnetometer, and it is the absolute workhorse of space plasma instrumentation. Every spacecraft should have a flux gate magnetometer. I don't build them, but they are the most valuable instruments in space, and they are incredible things. There's lots of details about how you do this. You would think that maybe you actually just measure this frequency and measure the second harmonic. Usually you don't do that. Usually what you do is you actually try to null things out by driving a current through this, and then you measure that current here. Lots of details to do with electronics. But basically what you're doing is you're driving a ferromagnetic material into and out of saturation, and you're looking at the offset because of the external field added to your drive field. So it's a really cool technique. I don't know who came up with it, but it is clever. All right, what about the other piece of Faraday's law? So back here we said, okay, we have a piece that looks like ddt of the permeability, but we also have a piece that just looks like ddt of the external field. You can also use that to measure magnetic field in a space plasma. And that is how a search coil magnetometer works. So here's a search coil magnetometer. It is basically just a permeable core of magnetic material with lots of loops of wire wrapped around it. The permeable core there is just to increase your gain, essentially. And then you just put this out in space. The ambient field oscillates, and you measure an EMF that is proportional to that oscillating magnetic field. It's the simplest instrument you could imagine. It is extraordinarily useful. Unfortunately, it does not measure the DC magnetic field. So usually when you have a search coil, you will also have a flux gate because you want to be able to measure both the DC and low frequency magnetic field, which takes a flux gate, and you want to be able to measure the high frequency field, which takes a search coil. There are other ways to measure magnetic fields. There are lots of very clever quantum mechanical techniques that you can use to measure magnetic fields. I'm just going to talk about one of them, which is called a proton precession magnetometer. So if you have a material which is specially prepared and you just kind of let it relax, what you can do is you can apply a drive voltage, and that will sort of flip all of your proton magnetic moments in one direction, and then as they relax, they will relax and they will spin around. They will precess, in other words, around the ambient magnetic field with a frequency that you can measure, and by measuring the characteristics of that proton precession, you can gain an extraordinarily sensitive measure of the magnetic field. This kind of measurement and other quantum mechanical based magnetometer measurements are really useful because they don't have any offsets. They're based on quantum mechanical principles, so if you can make the measurement, it tells you exactly what the magnetic field is. Now, the magnetic field, of course, might be contaminated by, a big magnet on your spacecraft or something like that, but it will tell you exactly the magnetic field. Flux gates have offsets, which you have to calibrate out, but quantum mechanical techniques do not. So why doesn't every spacecraft have a big proton precession magnetometer or a vector helium magnetometer? Because they're big and they're slow and they're expensive. Flux gates are cheap, they're small, they're fast, they're easy to operate, and so most spacecraft have flux gates. Top of the line spacecraft might have a flux gate and a proton precession magnetometer and use one to calibrate the other, but not everyone can afford that. All right, we can't leave out the electric field measurement. Bob Ergen would drive down here and hit me with a hammer.
He's in Yosemite.
He's in Yosemite, okay. All right, good for him. I would feel him judging me if I didn't talk about electric field measurements. Okay, so an electric field measurement is sort of the simplest measurement in space plasmas to understand and probably the hardest measurement to perform. So the basic idea of an electric field measurement is really straightforward. You measure the voltage across some difference and you divide voltage difference by distance and that gives you electric field. That's all there is to it. But it is a really hard measurement to make because if you remember my second slide in the presentation, these electric fields are so tiny. In like a reasonable plasma, the electric fields are millivolts per meter. So if you have a meter probe, you have to measure a millivolt difference across it. And that's really hard to do, especially because your probe is being bombarded by all the currents in the plasma, which are trying to change its voltage. And there's probably a sheath around your spacecraft where the voltages and magnetic fields of the spacecraft are perturbing things. And so it's just an extraordinarily challenging measurement to make. To measure a very small potential, the best thing you can do is have a very long baseline. So if you have a constant electric field and you're measuring voltage differences, the longer you make your baseline, the bigger the voltage difference, because the voltage difference is integral of E dot dx. So what you want is you want really long baselines. So the way to do that is what you see here. You have very, very long probes. So this is not to scale here, right? These probes here with the spheres on the end are actually 20 meters. So the way that you do that is you spin your spacecraft and then you deploy long, long wires with spherical probes on the end. 20 meters, so this spacecraft body itself is about a meter across. So imagine a spacecraft about this big and I've got a wire probe that's going out to the wall out there. That's kind of the scale of these instruments. And then I've got a wire probe going the other way, and I'm measuring the difference between those probes to give me a dV, which I can divide by that distance and get an electric field. And then I have another couple probes going that direction to measure things going that way. Doing this measurement is a dark art, and you can see all the electronics here that are involved. You want to get your probes as close to the plasma potential as possible, and that means you need to flow some current to them to keep them from charging up too much relative to the plasma. So there's an art and a science to figuring out exactly the right bias currents that you flow to your probes to keep them kind of close to the plasma potential, and then measure the difference between them. But when you can do it, you can get a very sensitive measurement of the electric field. There is another way that you can measure the electric field, which is to actually use particles to measure the electric field. So this is a very sensitive and clever technique, which sometimes works and sometimes doesn't. But the basic idea is that if you imagine a particle gyrating around the magnetic field, and then you add an electric field to this, you will have, in the last couple days, I think, talked about particle drifts in electric and magnetic fields. So the particle will execute a drift in that electric magnetic field, and if you can send out beams of electrons in different directions and measure where they come back to your sensor, you can back out the magnitude and direction of that drift. So you're basically sending out beams of particles and you're tuning things so that they go out and they come right back to your sensor after you've moved a little bit through the plasma, and that tells you the E cross B drift, and from that you can back out the electric field. So this works extraordinarily well when your plasma is kind of steady and homogeneous so that you can understand these particle orbits. Unfortunately, it breaks down when the plasma is inhomogeneous on scales comparable to the particle gyro radius, which unfortunately tends to happen in interesting places. And so we often go back to the very hard but very sensitive way of measuring it with long, long booms. Okay, this is the end of my grand tour. I want to wrap up with some kind of general remarks and not blow my time budget. So I haven't talked a lot about electronics, but you should remember that behind and below every one of these techniques that we have talked about, there is a set of electronics. So here are the electronics that I used for a charged particle instrument that I recently built for the Tracers mission. The exact details of these are not important, but there will always be a set of electronics that will be doing some of these kind of things behind the scenes in your instrument. There will be something like a detector. That detector will be producing something like a voltage or a current. You will be taking that voltage or current or whatever it is, and you will be digitizing it. You will be turning it into a digital number in some way. You will be putting a bunch of those digital numbers into a packet, a table if you want to call it, a set of digital numbers. You will probably be compressing that packet because telemetry is expensive and it's hard to send things down to the ground at the rate that our instruments can produce them. You will be taking that compressed packet and you will be transmitting it through the spacecraft radio down to the ground, where you will be trying to back all of this out. You will be decompressing that packet, and then you will be taking this list of numbers that you generated up here and trying to deconvolve that and apply calibrations and turn that into a measurement of the distribution function or the magnetic field or the electric field or whatever it is. And then you will be doing some kind of very, very clever scientific analysis on the results of that. Not a single one of these stages is perfect. At every one of these stages, there can be errors. There can be things that overflow or don't work the way that you want them to, or are just not exquisitely precise. And so at every one of these stages, you are stacking up errors, and you should always have those kind of in the back of your head when you're looking at a data set and trying to extract science from it. Other thing, yes?
By errors, do you mean errors or both?
Really both.
Sorry, I didn't mean to.
No, it's a good question, and I'm thinking about the best way to answer it. So there are inherently uncertainties in the measurement just because of things like Poisson errors and sampling resolution and things like that. So your measurement right off the bat has some amount of systematic and random errors in it, necessarily so, but then you're taking this product and you're feeding it through this whole chain, and every one of those things can introduce additional errors and uncertainty. So I guess what I'm trying to get across is that it's a whole chain of errors that you kind of have to stack on top of each other if you wanted to really do a full and complete error analysis. And ideally, a lot of that work is done for you by the instrument people in this deconvolution calibration step, but no data set ever generated in the history of space plasma physics has been without its foibles. And even a data set which is essentially perfect from here to here still may not be applicable to the regime that you're trying to use it in because of, you know, dynamic range issues or et cetera. A couple things to think about, which are, you can just barely see that color. Sorry for the use of yellow here. So let's imagine that you have a distribution function that you're trying to sample, and I'm just going to trace it out here with the pointer so you can see it. You have a distribution function which looks like this. Now imagine that you're going through and you're sampling this distribution function, and these are your measurement resolutions, and you have a measurement step here and you have a measurement step here. So this is sort of okay. You have measurement steps within the width of your distribution function and you're sort of resolving it. But what if your distribution function instead is very narrow like this? And then you come through with your measurement steps and you measure 0. But it's not because there's 0 there, it's because you're undersampled and you didn't actually catch the interesting thing in the distribution function. So there is a long history of charged particle instruments that have had holes in its measurement cadence, and things can fall in those holes. Oops, we missed it. Another thing to think about is deconvolution. So every instrument has a finite resolution. So if this is my distribution function here, again, sorry about the pale yellow, and I resolve it very well. I put lots of measurement steps across it, and each one of those measurement steps has a resolution which is small compared to that, then I can deconvolve that very well. But, and this is what I get out the back, and it looks something like what I actually tried to measure. But now imagine that I'm trying to measure a thing that's very, very narrow, and I sample it, I cover it, I don't have gaps in my measurement steps at least, so I don't miss it. But when I try and deconvolve this, I'm limited by the intrinsic resolution of my measurement, and my measurement is broader than the actual thing. So in an optical measurement, this would be called like a point spread function, right? But it works in other kinds of measurements too. In fact, it has recently been argued in a published paper that every measurement of solar wind ions ever made has under-resolved the distribution and over-reported the ion temperature. So beware. The other thing to always keep in mind is that there's a spacecraft in the way, and whenever you are making a measurement, the presence of the spacecraft is going to mess with your measurement. So it is not possible to create a spacecraft that does not affect the plasma around it, because your spacecraft itself is sinking currents from the plasma. It is charging up. It charges up because you've got plasma ions and electrons running into it. You've also got things like solar UV coming in and knocking photoelectrons off it. All of these things cause your spacecraft to charge up to a non-zero potential, and that means that your measurement is actually shifted from what it should be, because all the particles that you're measuring have come through a potential drop before getting to your sensor. So typically when you measure solar wind electrons in space, you have something like here where you have multiple components. This is actually the zero energy in the plasma, but all of these electrons have been accelerated by about 7 volts before they got to your measurement device, and so you're measuring energies that are higher than they should be. Additionally, you're measuring this whole extra population up here, which are not plasma electrons at all. Those are photoelectrons that have been produced by the spacecraft and then pulled back in by the positive charge of the spacecraft, and you can see that they actually dominate the distribution function that you measure. So this is particularly an issue for electrons, but in some situations it can mess with your ion distributions as well. So unless you have somehow created a magical spacecraft that floats at 0 potential relative to the plasma, you will always have these kind of effects. You will also have electromagnetic effects due to your spacecraft. So it is very, very, very hard to build spacecraft that do not have a magnetic moment. If you're interested, you can download a little app called Physics Toolbox to your phone, and you can go around and you can like scan things in your desk drawer. And if you wave your cell phone with Physics Toolbox on it above like a paper clip, what you will find is that a typical paper clip in your desk drawer has a magnetic field that can be like tens of thousands of nanotesla. So if you accidentally put a paper clip on your spacecraft, you're going to measure that instead of the solar wind magnetic field. So magnetic cleanliness is really hard because it's really hard to keep paper clips away from your spacecraft, even harder to keep, you know, a little screw or a bolt or something from getting magnetized and mucking up your whole measurement. That's kind of fancifully showed here by this spacecraft with a big dipole magnetic field around it. Probably it's more complicated than that. The other thing is that you're probably going to have AC sources of contamination on your spacecraft. So a common way to keep a spacecraft stabilized in space is to have what are called reaction wheels, which are basically little wheels that spin and they keep your spacecraft gyroscopically stabilized. If your spacecraft starts to tip over, you spin the wheel the other way. Conservation of momentum keeps your spacecraft upright. A reaction wheel has about 30 little permanent magnets in it and a rotor, which is typically made out of magnetic field or a magnetized material, and it spins that reaction wheel at something between 0 and several thousand RPM, and that creates a magnetic field which looks something like this. And if you analyze that in the spectral domain, you see all these fun little reaction wheel tones that drift up and down through your measurement. And the Whistler wave that you're trying to resolve is sitting underneath that. So there's always a spacecraft in the way. So a couple of key takeaways. I think I'm actually miraculously right on time. So first of all, the measurement devices themselves can be just as complicated as the system that you're trying to analyze. So actually the physics of measurement devices is a fascinating subject in its own right, and it is physics. But it gets in the way of the physics that you're all trying to do using the data from those products. So be an informed user, understand that the device is not perfect, understand where its limitations are, where the assumptions break down. Depending on what you're trying to measure, you might have limitations due to sensitivity, dynamic range. You might not have enough sensitivity to measure the low end, or you might saturate at the high end. There's always a regime in which the instrument just gives it up and won't do it anymore. You might be limited by resolution. I showed you a couple of examples of how you can miss key features in the distribution if you don't have enough resolution. If you don't have enough counting statistics, then you can be limited just by Poisson counting statistics. We talked about this a little bit, but there's all kinds of systematic errors, offsets, backgrounds, things like that that you need to calibrate out. Ideally, you've done measurements on the ground to calibrate all of this, but actually, having worked in a lot of calibration laboratories on the ground, I'm going to tell you those are not perfect either. So beware. And then even if you had the most perfect instrument ever constructed and you had perfect calibration and everything, that instrument is on a dirty, noisy spacecraft which has its own magnetic and electric fields and is charging up and repelling particles and creating whole new populations of particles, and it's complicated. I think maybe a few minutes still for questions, but I'll let Nick.
So first let's thank Jasper. We also have some built-in questions just before.
Okay.
So I think what we'll do now is let's see a couple of clarifying questions. Like is something that quickly, and then
So how do you go from current measurements to velocity distribution functions? And like once you have the velocity distribution functions, how do you discriminate between like the particle populations, especially like when they're overlapping one another?
Yeah, it's a really good question. So depending on what kind of measurement device you're using, you're probably doing some kind of scanning. So if you have like an RPA or a Faraday cup or something, what you're doing is you're scanning the energy. So that's going to give you current measurements in different windows. And then what you're going to do is you're going to take those and you're going to use those to construct some kind of a reduced energy spectrum. So it is not going to be the full glorious F of 3 components of position and 3 components of velocity, right? It's going to be a reduced version of that, which is basically a cut through F along the direction that your measurement aperture is going. And then, you know, if you're lucky, perhaps the spacecraft will rotate around and it will allow you to scan out different directions or things like this, but maybe not. But at least you'll have something like an F of E. And then you can start to analyze what that F of E is made out of. So if you have some, you know, kind of a priori information about your plasma, like you know, okay, I'm in a particular region where I know that this plasma is going to be made up of hydrogen and a little bit of helium, and I expect the hydrogen and the helium to actually be flowing at the same velocity, and therefore if I'm measuring energy per charge, the doubly ionized helium will have twice the energy per charge of the hydrogen, and so I expect to see 2 peaks. And then you can query and see, okay, does my measured distribution have 2 peaks like I expected? No. Okay, go back to square one, think of new assumptions. Yes, now maybe you can start to fit some kind of a model to it. So, you know, a typical model that you might use would be, say, a convecting Maxwellian, and you might try to fit to the density and the temperature and the bulk velocity of that Maxwellian. And if you're very ambitious, you might use a superposition of a couple Maxwellians to try and detangle overlapping populations. So this is kind of the game.
Hello, yes. Okay, so the question that I'm going to ask you already answered most of it, but I'm still curious about it. That as you mentioned, the instruments themselves can have some kind of bias or contamination. So as you said that, yeah, be aware of the measurements that you are reading. But I'm just curious that can the instruments themselves come with some sort of like tolerance level or some sort of uncertainty level in the measurement data that when we are analyzing it, we can take that into consideration?
Depends on how good the instrument team has been to you. So I will say that when I make data products for people to use, I like to include some of the very low-level information in there so that people can do this. So for instance, the scientific data product from a particle instrument is the distribution function, but that distribution function was created by taking raw counts and applying various scaling values and things to that. Now, what I like to do when I create a data product is include those raw counts as well as the calibrated distribution function. And then that allows you to go in and say, okay, I understand how Poisson errors work. I can see that, you know, in this measurement bin, you only have 3 counts. I probably don't think that that is going to be a very precise measurement. Now, not everyone does that. Some people like to say, I'm going to produce the greatest data product ever, and I'm just going to give you the final distribution function, and that's all you get. But I think that is shortchanging the user, because I think that the user will come up with better ways to analyze the data if you give them the information. So that's a little bit of a self-serving answer, but that's the way I like to do it.
Thank you.
I saw a couple more hands. So we got one here, and then we'll go to the front table.
So you have talked about this top hat analyzers, right? So I just want to know, in the top hat analyzer, you have like, is it the particles are coming all through the 360 degrees in a 2D plane? So you're collecting from like 360-degree particles in that.
Unless there's some sort of collimation or something that you put to stop that, yes. So the top hat analyzer intrinsically has a 360-degree field of view, but then down below that you're going to put a detector, and you can choose where to put your pixels under that detector. So if, for instance, you already know the particles are all only coming from a 180-degree field of view, maybe you only put pixels over half of the area underneath that. But in principle, you can measure a full 360. You will have a few little blockages in there because of, you know, the posts that have to hold up the top hat and things like that, but those are hopefully small.
So you mentioned that the different particle detectors work best in different densities. Could you give me a sense numerically, like what those density ranges are? Like how low of a density do you need for a solid state detector, for example?
It's hard to give you a single answer to that because it matters how fast the particles are moving. So there's, you know, it's a multi-dimensional trade space that they work in. I will say that as a sort of a rule of thumb, current measuring devices tend to work better in densities of, you know, hundreds, thousands, tens of thousands per cc. Particle counting devices tend to take over at lower densities. Solid state devices tend to work best at higher energies because you always have some kind of a dead layer, and so unless you do like a big 15 kilovolt pre-acceleration or something, you need 30 kilovolts just to get through your dead layer. And so solid state detectors are well tailored to the wings of your distribution. And that's also a good thing because solid state detectors tend to be slow. So if you tried to measure, say, the solar wind core with a solid state detector, you would just instantly saturate because your detector electronics can't keep up. So that's sort of, you know, rough rule of thumb maybe, but there are details to how you build and design things. And if you put apertures in front of them to collimate and, you know, things like this, you can tweak the regime.
All right, so if you've got more questions, we'll write them down and we'll do them during the Q&A time before lunch. And of course, Jasper will be here